In this video, we're going to be talking about the binomial distribution, and we're going to kind of get to a point where we can actually come up with a formula in order to calculate probabilities based on binomial random variables. So let's talk about what a binomial random variable is and kind of how it works. To do that, we first need to talk about Bernoulli trials. So a Bernoulli trial is a trial where each trial is either a success or a failure. So it's kind of a black and white, one or the other kind of system, kind of a binary system. So if you're familiar with computers, 0 and 1s, that's the idea of a Bernoulli trial, is that it's either a success or a failure, the light switch is turned on or off, one or the other, but not a combination of both. So in order to have a binomial setting, you have to have 4 different criteria met. And to remember those, there's this acronym which we've come up with, which is called BINS, so B-I-N-S. The B stands for binary. So by binary, we mean that all the trials are Bernoulli trials, so it's either a success or a failure. The I stands for independent, so the trials have to be independent from one another. In other words, one trial cannot affect the next, and so on. The N stands for the number of trials, which have to be a set number of trials. So you're going to do whatever this is a set number of times. It's not as if you're going to sit there and continue to flip a coin until you get heads. You're going to flip that coin for, let's say, 10 times. So it has to be a set number. Finally, S for success means that the probability of success does not change, that it's a constant probability of success. When I roll a dice, I always have a 1 out of 6 chance of rolling a 5. So the binomial random variable is any random variable which satisfies all of those conditions. So if it satisfies those 4 conditions, we consider it to be a binomial random variable. We're going to be using N and P frequently throughout the notes today as well as in the next section. N represents the number of trials, P represents the probability of success. And then K, or X, will be representing the number of successes. So in order to have the mean and standard deviation, we've got a couple of formulas for those. For the mean, or mu of X, we're going to take N multiplied by P. And for standard deviation, we take N multiplied by P, multiplied by 1 minus P, and take the square root of that. So let's work through a few examples. In this first example, we're going to look at 3 scenarios and try to decide if the random variable would be a binomial random variable. So in example A, we're rolling a fair dice 10 times, and we're going to let X be the number of 6s. So for the B, for binary, I'm just going to put that as B question mark for our bins. And we need to decide, are these Bernoulli trials? Are we going to be able to classify a success and a failure? Well, it looks like X is the number of 6s, so it looks like 6 is going to be a success. And anything else 1 through 5 is going to be a failure. So yes, we do in fact meet that first criteria. The next one is I for independent. Are the dice rolls going to be independent, or does knowing the outcome of one affect the next? And in fact, they are independent of one another. It's not as if rolling a 5 means that you're more likely to roll something else the next time. For the N, do we have a fixed number of trials? Well, it told us that we were going to roll the dice 10 times, so N would be equal to 10. So yeah, we do have that criterion met as well. Finally, for the S, do we have a fixed probability of success? Well, the probability of rolling a 6 is always going to be 1 out of 6. So yeah, in fact, this is a binomial distribution. Let's take a look at B then. So on example B, we're going to shoot a basketball 20 times from various distances on the court, and we're going to let Y be the number of shots made. So first off, is this going to be binary? Well, if you make the shot, that's a success, or if you miss the shot, that's a fail. So yeah, it is binary. You're either making the shot or missing it. For I, are these shots independent of one another? Well, yeah, I would say they are, unless you get tired, but it's not as if one shot is going to affect the next shot. So yeah, I would say that they are independent of one another. For N, do we have a fixed number of trials? Well, we're going to shoot the basketball, it said 20 times, so yeah, we do have that. How about for a fixed probability of success? So what is the probability that we make the shot? And here's where we run into a little bit of a problem. And the big problem is that you're shooting it from various distances on the court. And for those that are familiar with basketball, and even if you're not familiar with basketball, the idea of shooting a layup versus shooting a half court shot, you're probably more likely to make the layup than the half court shot. So I would not say that the probability of success is going to be the same each time. So that's not going to work. That means that this is not binomial. All right, let's go ahead and look at C then. So observe the next 100 cars that go by and let C be equal to color. So for the first part, for binary, for success and failure, well, they didn't give us a lot. They just told us that C was color, and we're recording, I guess, the color, but how do we know if it's a success or failure? We don't. So actually, right away, it does not meet that criteria for it being binary, and so we're going to say that this is not binomial. All right. The rest of this section of notes is going to lead us to a formula that we'll be able to use to calculate binomial probabilities. In order to help us see that, we're going to look at rolling a dice. So in many games, when you roll a dice, rolling a 6 is desirable. Obviously, 6 is usually the highest number, so rolling a 6 is usually good. The probability of rolling a 6 when you're using a fair die is 1 out of 6. No surprise there. If x is the number of 6s that you get in 4 rolls of a fair die, then x would be binomial with n is 4 and p is 1 over 6. In other words, we already know that this is binomial. We're being told that. We could check it if we wanted to, and it would in fact show that it is binomial. In fact, we even know our parameters. We know that the number of trials is going to be 4 and that the probability of success on each trial is 1 out of 6. So then we want to know, what is the probability that x is equal to 0? In other words, what is the probability that we get no 6s? In other words, what is the probability that all 4 rolls are not 6s? In other words, that the first one is not a 6, and the second one is not a 6, and the third one is not a 6, and the fourth one is also not a 6. Well, let's think about that. The probability that you don't roll a 6 is going to be 1 minus the probability that you do get a 6, or you could just think about that as being that there are 5 other options besides a 6 that you could roll. In other words, to find this probability, we would be taking 5 out of 6 multiplied by 5 out of 6, and actually we're going to end up multiplying by 5 out of 6 all 4 times, which you could also write as 5 over 6 to the power of 4. And as a decimal, let me go ahead and type that into our calculator. If we take 5 over 6, that's 0.83. Raise that to the power of 4. As a decimal, that's 0.4823. We'll go out to 4 decimals. All right. To continue this investigation, we're next going to look at what is the probability that we get x equal to 1. In other words, the probability that we get 1/6 out of 4. Well, let's see. That would be the probability, if we were to write this out, that you maybe rolled a 6 on the first one, but then didn't get a 6 on the second one, and then you would have to get not a 6 on the last 2 as well. And so in order to write those out, obviously the probability that you get a 6 is 1 out of 6, multiplied by the probability that you don't get a 6 is 5 out of 6, and again we'll use that for the other 2 as well. So then here's what that formula, or what this equation looks like. In other words, we're taking 1 out of 6 multiplied by 5 out of 6 to the power of 3 this time, since it's only 3 of those. So let's see what that ends up being. We're going to take in parentheses 1 out of 6 multiplied by, in parentheses, 5 out of 6 to the power of 3. And so as a decimal, that ends up being 0.0965. Now, something that you maybe were thinking about that we'll now discuss is, why did the 6 have to come first? Why couldn't we have rolled this 6 in the second spot, or the third, or the fourth? In other words, it's not as if this is the only place where this could happen. We could also have had that we rolled something else. So not a 6, then the 6, then another not a 6, not a 6. We could also arrange it like this. And we could also arrange it like this. In other words, there's 1, 2, 3, 4 different ways that we could get this probability, meaning that we actually need to take this percentage that we just found and multiply it by 4. And so when we do that, take our answer that we just got and multiply it by 4, we find out the probability of getting 1/6 is actually quite a bit higher. It's actually 0.3858. Let's continue to do this with a few more examples. In fact, let's do it for all possibilities. So the probability that x is equal to 2. So the probability that we get 2 6s. And again, at least at first, let's put those 2 at the beginning so that we're getting a 6, and then a 6, and then a not a 6, and then a not a 6. So that's going to be, let's see, probability that it's the 6 is 1 out of 6, and we want that to happen twice. Not a 6 is 5 out of 6, and we also want for that to happen twice. So really what we need to do then is figure out how many ways can we arrange that to make this work. Well, you could have the 2 6s at the beginning, and then 2 other numbers. Or you could have it 6 at the beginning like this. Or you could also have, let's see, 6 at the beginning and then a 6 right here. We could have nothing at the beginning, 2 6s in the middle. We could have something like this. Let's see, something like this. And I believe that's all of our possible combinations. That comes out to a total of 6 different ways this time that you can make this happen. So let's go ahead and see what that probability is. So that would be in parentheses 1 out of 6 to the second power multiplied by 5 out of 6, also to the second power, and then multiply all of that by 6, gives us a probability of 0.1157. Now here's the point where I'm hoping that you've started to notice a pattern, so that when we want to find the probability of 3 6s, we can maybe take a little bit of some shortcuts. So if we want 3 6s, that means we want the first 3 possibly to be 6s, so that would be 1 out of 6 to the third power. And then the other roll to not be a 6, so that would be the 5 out of 6 to the first power. Now I'll go ahead and help you out. There's 4 different ways that you can get that to work out, and so that's where we need to multiply that by 4. So again, let's type that into our calculator. 1 over 6 to the third power this time, multiplied by 5 out of 6, multiplied by 4. And that's going to give us a probability of 0.154. Or 0.0, let me go ahead and get that decimal in the right place. So 0.0154. Okay. Cool. So really we just have one last scenario that could possibly happen, which is the probability that all 4 are 6s. So the probability that you get all 6s, that means that now that 1 out of 6 chance you need to have happen all 4 times. Really what that also means is that 5 out of 6 chance, we really don't have to write it, but that would be happening 0 times. And if you think about it, there's only one way for that to happen. So this one should be pretty quick to find. Just take 1 out of 6 and raise that to the power of 4. And it's probably not very likely. Going to be a very, very small decimal. Going to be 0.0008 when you go out to 4 decimals. Okay. Now, obviously, this is great. And this gives us an idea of kind of how the binomial distribution works with these probabilities. But it's going to be nice to have some kind of a formula that we can use to do that. The first thing we need to kind of talk about is how we're coming up with these numbers of 1, 4, 6, 4, and in the case of 0, we would have had a 1 out here since there was only one way for that to happen. So we need a way to generate those numbers, and in fact there is a way to do that. It's what's known as the binomial coefficient, and we write it as NCR, where N is the number of trials, and R is the number of successes that you want. So in other words, r could also be x in our case. Now there is a formula for this, but I just want to show you how to do that on your calculator. So as an example, let's say we were rolling our dice. Again, we had 4 trials, and we wanted to know how many ways could you arrange 2 successes, which we've already found was this number 6, but let's go ahead and see how the calculator can find that for us. It's under the Math button, and then under Probability, option number 3 will say NCR. From there, you'll type in the 2 numbers that you want, so that would be 4, and then choose 2. So oftentimes when we read this, we'll read it as 4 choose 2, and that'll tell us that there are 6 ways to arrange 2 successes in 4 trials, which is kind of nice, because especially when you get to larger things, like if I wanted to know out of 20 things, how many different ways can I arrange 2? Well, I probably don't want to write it out this way. That's going to take a lot of time with 20 numbers and 20 spots to fill that in. But with the calculator, if we go to Math, over to Probability, choose that third option, type in 20 for our number of trials and 2 for our number of successes, we can find that pretty quickly to be 190 different combinations that work. Now, the rest of the formula, let's talk about that. So the probability that x is equal to some number of successes, which I'm just going to call that, let's just call that k, is to do this. We're going to take n choose k, so that would be the number of ways that we could arrange that many successes, multiplied by the probability of success to the power of k, multiply that by the probability of failure, so 1 minus the probability of success, to the power of n minus k. Where, just to remind you, in this scenario, n represents our number of trials, p represents our probability of success, and k represents our actual number of successes. So let's just do one example using that formula so that we can see where it's useful, and then we'll be done. So let's kind of stick with our rolling the dice example. We're going to roll a dice 10 times now, and we want to know what the number of, let's say, 5s are that we get. And so what is the probability that we get 4 5s out of 10 rolls? Well, using our formula, we would plug in our numbers, so n would be 10. Choose, we want to have 4 successes, so 10 choose 4. Multiplied by our probability of success, which the probability of rolling a 5 is going to be 1 out of 6. So we're going to multiply that by 1 out of 6 to the power of the number of successes we want, which is 4. And then multiply by the number of failures, so that would be the probability of failure is 5 out of 6 in this case, to the power of n minus k. Well, if there were 4 successes, 10 minus 4 means that there would have to be 6 failures. And now instead of having to write it all out, we can actually just use the formula to find that. So we'll go to Math. We'll go ahead and find probability. First find the 10 choose 4. And so 10 choose 4 tells us that there are a total of 210 different ways that we could arrange 4 successes in 10 trials. So we're going to take 210 multiplied by our 2 fractions to those powers. So our answer multiplied by, in parentheses, 1 out of 6 to the power of 4. And then multiplied by 5 out of 6 to the power of 6. And so that's going to be equal to 0.0543 when you go out to 4 decimal places. So as before, we had to kind of think it all the way out. Now we've got this convenient formula that we can use in order to find probabilities very quickly. Next time, we'll be talking about the binomial distribution once again. We're actually going to have some calculator commands which will do this formula for us, which is great. Until then, have a great rest of your day.